And are there any questions on that? Everyone go with the final? Everyone go with all the stuff? Nice.
The
Yeah.
last day of lecture.
Oh, say that again. I'm sorry.
When's like the last day of live lecture?
Oh, I think my last lecture is the Monday before the final. So this is a Thursday, and whatever the Monday before that is. So the 15th? Is that right? Maybe. That'll be the last live lecture. Then that Tuesday is reading day, and the Wednesday is the first day of finals, and we are on the second day of finals, the Thursday. Okay? Also, solutions to those practice problems will be posted Saturday. So, just FYI. Any other questions? All right. We are going to start with a note. And I think many of you already know this, but I'm worried that I might have glossed through it when I was talking about the binomial. And that is what this thing is. It's called the binomial coefficient. And I wrote one version of the binomial that used this coefficient. It's basically just shorthand for this. Not basically, it is just shorthand for this. Which sometimes people also say n choose k when they describe it. Which gets into something called permutations and combinations, which we're not actually going to cover in this course. Suffice to say, this is if you saw me use that notation, this is what it is. If you were at all confused, I just wanted to make it absolutely clear. And I also wanted to, I think all of you should have seen this in algebra, but just in case, this exclamation point is called factorial, right? And it is x times x minus 1 times all the way down to times 2 and times 1. So, for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. So if I glossed over that a little fast, I apologize. Some people mentioned a few things to me that made me think, maybe I shouldn't have just assumed everyone had seen this before. So if you have, sorry to waste your time. Anyway, so our first topic today is the Poisson distribution. And for those of you who are French speakers, this is not supposed to be about fish. Poisson means fish in French. It's actually just somebody whose last name was Poisson. His name was like, I guess his name translates to like Jack Fish, which I think is kind of funny. But it has nothing to do with fish. It instead is just another discrete probability distribution that if we can recognize a certain problem as fitting into this type of problem, this distribution is going to come with sort of a canned formula for calculating probabilities. So let us explore the Poisson distribution by means of an example. There are 8 million people, I'm going to say around 8 million, in New York City. How many individuals might we expect to be hospitalized for heart attacks each day? So this is a question that we can actually get some historical context for. So according to a historical average, so just looking at over the last, I don't know, maybe like 20 years, just look every single day, how many people were hospitalized for a heart attack each day. Hospitals have very excellent record keeping. This is something we could certainly calculate. According to historical average, I'm going to say it is 4.4 people per day. So if I were to look over a number of years at the number of people each day, I would say that over the long term, it averages out to be 4.4 people a day. But no, this can still vary day to day. So actually, I have a, let's see, I have a histogram. So what is this? This is, x-axis is number of days. X-axis is number of heart attacks. And this is NYC data over 1 year. So how would we interpret this histogram? This is saying that there were days that how many days were there only one, was there only one heart attack observed? And the answer to that is it looks like maybe around 18 days. So 18 of the 365 days in the year, there were days that only one person was hospitalized for a heart attack. Maybe of the 365 days of the year, it looks like about 50 were days when there were only 2 heart attacks, 2 people hospitalized for heart attacks, right? You can see that this distribution, it describes that on different days, I might have more or less than, well, 4.4, but it averages out to 4.4. Do we see this? Yeah? Okay. So my question for you is, does tomorrow have 2 M's in it? Tomorrow. Does it have 2 M's or 1 M? Thanks. 1. What's the probability that 4 people are hospitalized for heart attacks? So this is a very different question. We aren't asking about the long-term average. We're asking about tomorrow, based on what I observed over the last year, what is the probability that tomorrow I will observe 4? And this is something that we can answer with a Poisson distribution. So before I give you the formula, let me first give you a better definition of what a Poisson is. We say a random variable follows a Poisson distribution when it asks how many events occur in a fixed time interval. And the population that generates the events is large. All right, so this is our large population that is generating events is New York City, every single person in New York City. The event that we're trying to observe is whether or not a person shows up to be hospitalized for a heart attack as a consequence of a heart attack. And our fixed time interval is we are just thinking about how many times it happens in a given day, right? So each day, how does it happen? So let's talk about the formula. Let x be the number, the random variable, the number of heart attacks in New York City tomorrow that are hospitalized? Okay. Then probability that x is equal to k, which is the probability that we observe k heart attacks, is equal to lambda to the k. So this Greek symbol is called lambda, e to the negative lambda over k factorial, where lambda is equal to the rate at which the events happen, or the average number of occurrences in a mostly fixed population for a fixed interval of time. So in our example, lambda is equal to 4.4. It is our best guess at the rate at which people have heart attacks. Every single day, they come at a rate of 4.4 per day. All right, so these are sort of the ideas of Poisson. Let's try to see if we can maybe make it illuminated a bit with an example, which is, we'll just use the example that I proposed at the beginning. So lambda is equal to 4.4 here, and we want to know the probability that tomorrow we observe 4 hospitalizations for a heart attack, right? X equals 4. So we just plug it into our formula. It's 4.4 to the 4th, lambda to the k, times e to the negative lambda, 4.4, negative 4.4, over k factorial, which is 4 factorial. And I went ahead and plugged this in myself. You got this. You're welcome to check my work, but note that with our formula, calculating the probability is relatively easy. We don't have to think about sample spaces and figure out proportions and do all that complicated stuff we did last week. We instead just say, this looks like a Poisson process, a Poisson distribution. I'm interested, I know what my lambda is, my rate, and I am interested in knowing what is the probability that there are 4 occurrences tomorrow. And that's how you would do it. And you would get this probability as your answer. That's the probability of 4. Yes?
Does it say 4.4 to the power of what? Sorry, I just missed.
Oh, it might be a little, I think there's a comma here. It's 4.4 to the power of 4.
Oh, okay.
Okay? Nice. So, just like how I gave this to you for the geometric and the binomial, I think I gave it to you for the normal as well. When x is distributed, Poisson, we know the formula for expected value. I'm just telling it to you. It's equal to lambda. It's a very easy formula. And actually, something that's really cool, I think is really cool about this distribution, is that the variance is equal to lambda as well. It's a very special distribution where the expected value and the variance are actually equal to one another. So, I don't know, maybe you can think about why that is a little bit on your own time, but it's always sort of, I don't know, it's always sort of fascinated me about the Poisson, about the fish, you know. Anyway, so this is the Poisson distribution. It is another distribution where if you can realize that something looks like it's following a Poisson distribution, you just have a formula to calculate every single probability you would ever want, okay? So that's Poisson. I have one more discrete probability distribution I'm going to show you next. Are there any questions first off on the Poisson, though. No, we're good? All right.
Sorry. I had a question.
Okay, what's up, Leo?
So it's like a large population. Is there
Yeah.
is there like a specific quantifier for what is considered large?
Large? That's a great question. It depends on in what situation you're working. So you remember when I said when we want to get independent random samples of a population, our sample has to be less than or equal to 10% of the population to get that approximate independence. So I would say this, maybe don't quote me too hard on this. So one of the things about the Poisson distribution is that technically we need each of the events to happen independently of one another. And that the reason I say that use a large population is because with small populations, these events don't really happen independent of one another, right? If 10 people have a heart attack in in one day and your population is 20, your probability of having people show up with heart attacks tomorrow goes way down, right?
Mhm.
So that's why I say, I think because there's a lot of nuances to the Poisson distribution, and I'm giving you kind of like a blithe, a kind of cursory look at it. So rule of thumb, think like something so large that events happening one day don't affect them happening at another day. So New York City is so big, if 5 people get a heart attack in a day, there's so many other people that it doesn't really affect my probability of more people getting it tomorrow, right?
Mhm.
So I don't know, 1 million to give you an ad hoc estimate. If you had a smaller population and you wanted to do a Poisson, you would have to do a lot more research and justify as to why you're doing the Poisson, and that's a little bit outside of the scope of what I was going to teach on it. Good question, though. Okay. All right. Any other questions? No? All right. Negative binomial. So last discrete distribution. We're getting so close. I'm sorry for people who love probability, but for people who don't, we're getting so close. The negative binomial distribution. So, recall that the geometric distribution describes the probability of observing the first success on the kth trial. So this was our last lecture video. The negative binomial distribution is more general. It describes the probability of observing the rth success on the kth trial. So if that was a little esoteric for you, take a step back for a second. So an example of a geometric is if I were to flip a coin until I got heads, right? What is the probability it takes me 3 flips before I get heads? What is the probability it takes me 4 flips to get heads? The geometric distribution answers these sorts of questions. Now we're kind of saying, well, wait, what if I'm not interested in waiting until I get 1 heads, but I'm way interested in how many trials it takes me to get 3 heads? So how many times do I have to flip before I get my 3rd head? The negative binomial distribution can answer questions like that. So let's do an example. at UNC. Nearly 20% of undergrads are first generation college students. Suppose you choose students randomly one at a time. So I'm grabbing a student, I'm grabbing another student, and I'm just like one by one sampling students randomly from UNC Chapel Hill. What's the probability that the fifth first generation student I choose here, I think I want to say this a little bit differently. First generation student I select happens on the 10th student I randomly sample. Right? So what is the probability that it takes me 10 trials before I select 5 first generation students? And just like all the other ones, there is a formula for this. Let X be how many trials it takes you to observe the fifth first generation student. Then the thing that we want is the probability that X equals K, probability that our trials equals K, equals the probability that the rth success is on the kth trial. Equals k minus 1 factorial over r minus 1 factorial, k minus r factorial, p to the r, and 1 minus p to the k minus r. And let me go ahead and define all these variables I'm throwing at you. So p equals the probability that an individual trial is a success. So success in this case is whether it's success is I selected a first gen student. R is the number of successes we wish to see. So I'm going to keep selecting students until I get my fifth first generation student. So that is R, 5. And then K is the input. What's the probability that we have to observe K trials to get R successes? Right? So if I want to know the probability that it takes me 10 tries before I get my 5th first generation student, then K would be 10. So let's use our example from up above. I want to know the probability that it takes me 10 trials to get 5 students. So K is equal to 10, probability of X equals 10. And I just plug it into the formula. So this was K minus 1 factorial over R factorial, K minus R factorial, just 10 minus 5. Then the probability of success, which in this case was 0.2, I believe, right? We had a 20% chance of choosing a first gen student by randomly choosing students at UNC. So 0.2 to the R, which is 5, and then 1 minus 0.2 to the 10 minus 5. So I could write this out a little bit more. This is going to be 9 factorial over 4 factorial, 5 factorial. 0.2 to the 5 and 0.8 to the 5, which you may check my work, but I went ahead and calculated this and got. So with probability 0.013212, it will take me 10 trials before I observe my 5 first gen students. If I were to do this experiment over and over again, 1.3212% of the time, it would only take me 10 trials to find my 5 first gen students. Okay? This is another just sort of plug and chug. I'm going to make a few more points about the negative binomial, but now is a great time to interject. I've been throwing a lot of formulae at you over the last couple of lectures, and that's fine. There's a bunch of different things that we need to know and you need to sort of have in your arsenal whenever you approach these probability problems. However, on the lecture video, which is now posted, I'm going to walk you through how to make sort of a cheat sheet of all of these different probability distributions. I think you've already done all the hard work of actually by hand calculating stuff, and from this point forward, I'm going to expect you to just be able to realize it's negative binomial, for example, and then just plug it all into Excel and have it do all the work for you. So if doing all the arithmetic was really sort of the worst banal thing that you could possibly do, know that it ends as soon as you go through this next lecture video. I'm going to just teach you how to do it all in Excel, and we'll let the computer do the hard work for us. But that does mean that the hard work is now going to become, if it weren't already, being able to look at a problem and realize which of these distributions describes this problem. So that will hopefully come through practice, which you're going to get more of it on this next homework. Okay. So this is the negative binomial distribution. There's an important point for me to make about it. And that is, notice that if we wanted to know the probability of our first, it's confusing, I apologize, first gen student happening on our 5th draw, well, we could use a negative binomial to answer this question, right? So we are only interested in r equals 1. We want to know when the first one happens, not the second, the third, or the 5th. Our k in this case is 5. We want to know the probability that it takes us 5 trials until it happens. And our probability of any individual success is 0.2, right? So we could very easily plug this into our formula. This is probability of x equals 5 equals k minus 1 factorial over r, oh goodness, I shouldn't speak out loud, r minus 1 factorial k minus r factorial, and then p to the r and 1 minus p to the k minus r, which would reduce, this actually reduces to 1, so it would be 1 times 0.2 to the 1 times 0.8 to the 4, which is, I calculated it, is this. So this is that probability that it takes us 5 draws before we see our first generation student. But what I want you to note is that this is the same thing as the geometric distribution. Recall that we used the geometric distribution to model how many trials it took until our first success, which is specifically what this question up here is asking. We were able to plug into the negative binomial, but if we were to do the same thing with the geometric, so what was the geometric? We needed to know k is equal to 5. This probability takes us 5 trials until the first success, and probability of an individual success is 0.2. Well, if I were to plug this into the formula for geometric distribution, it would just be 0.2 to the first minus 1 minus 0.2 to the k minus 1, which is equal to 0.2 to the 1 times 0.8 to the 4. And look, they're the same thing, right? The negative binomial is a more general form of the geometric, and if you were to put r equals 1 into the negative binomial, it would just become the geometric, right? Geometric's like the easy version. Our negative binomial is the more generalized, the more complicated version. But they reduce to each other, which is kind of cool. So I'll write that out explicitly. The negative binomial is a more general form of the geometric. All right, so that is the negative binomial, and just like all the other ones, I'm going to tell you when x is distributed x is distributed negative binomial. There are also these formulae. If you want to know the expected value, the long-term average of a random variable that is distributed negative binomial, it is just r over p. Just plug it into this formula, it's not that hard. And the variance is this. Okay? So one of my students in my previous section asked me to put together a sort of formula cheat sheet, and I will. You just need to give me until the middle of the week, and I will let you all know when I post that. So if I'm throwing too many formula at you, I apologize, but we'll try to organize it as best we can, not only via that cheat sheet, but in the upcoming lecture video. So any questions on the negative binomial? Nope, straightforward, just another equation. Well, it is our last discrete distribution, so hope we can organize them all. I have a note I want to make about some of the discrete, and then we're going to move on to a continuous. So wow, that was a long title. Okay. So there are certain things that all three of these particular discrete probability distributions have in common. Each concerns multiple independent binary events that happen with equal probability. And I'm going to go into what I mean by each of these right now. So all of them have independent trials. And what that means is the trial of one, or the success of one trial shouldn't affect the rest. An example of this is each flip of a fair coin doesn't affect the outcome of other flips. Right? So let's think about, okay, so the binomial, we had sort of a fixed number of trials. And the idea is that each of them don't affect one another. They all happen independently of one another. And that was the same thing with the geometric. We have these trials that go on and on and on and on. And every single time we flip the coin, it doesn't affect what happens to the next flip. That was the same thing with the negative binomial. We keep flipping coins. We keep having these trials, one after another. And whether or not they are a success doesn't affect whether or not future or past ones are successes. The other quality, which was binary, is that each trial has one of two possible outcomes: success or failure. So each coin flip is either heads or tails. So again, think about the distributions that we're talking about. The binomial has one of two options. What was our original example for binomial? Maybe it was like passing or failing a test. You either pass the test or fail the test, right? For geometric, if we're waiting to see until we get that first generation student, every single time we randomly pick a student, they are either first gen or they are not first gen. It is this idea of yes or no, a binary. That's what it's called. The final thing is equal probability. The success of each trial happens with the same probability. So each coin flip is heads with 0.5 probability, right? Every single time we picked a first generation student, the probability, every single time we picked a student, the probability of that student being first generation was 0.2, and that didn't change for every single trial. Every single time we flip the coin, the probability of heads is 0.5, and that doesn't change every single time we flip the coin. So that's the third quality of all these distributions, is that the probability remains constant. Okay? So these are three things that are required for these distributions. These are three things that these distributions have in common. Just very specific qualities of these things that we have gone over. All right, any questions on these? All right, well, with that, we are outside of discrete distributions. I want to talk about one other thing, which is that we've actually sort of kind of gone over, but we haven't necessarily gone over it in this context. So let's talk about the uniform. A random variable x can take on discrete or continuous values. We've been doing a lot with discrete. Which are when x can be equal to 1, 2, 3, 4, etc., etc. So in the case of our binomial, we had 10 trials. How many of them were successes? That is a question that is, okay, 1 was a success, none were a success, 2, 3, 4, 5, 6. We didn't have 4.5 successes, right? It was very much a discrete number, an integer, or I guess in that case, a whole number. And most of these that we've done so far recently, like the Poisson, the negative binomial, the binomial, the geometric, these are all discrete probability distributions. Continuous means that x can take on any real number. So our example of this was when x is normally distributed. So if it was like mu is equal to 50, sigma is equal to 5, our x value could take on 45, it could take on 44.7, it could take on any of these numbers in and around our mean. And as a consequence, we have to model it with a continuous distribution rather than a discrete. So today what I want to talk to us about is so we've been looking at these probability problems, right? We've been saying, this is a bunch of trials, maybe n trials, and I want to know what's the probability I get 3 successes in n trials. So when you're presented with this probability problem, you can model it as, in this example, a binomial distribution, and then you can use that model to calculate probabilities really easily. Now I'm going to introduce a situation where we might want to model it with a uniform distribution, which is a continuous distribution, and then use it the same way that we used our continuous distributions to easily calculate probabilities. And this should look familiar. We've done continuous distribution probabilities since the beginning of this class, but now I'm talking about it in the context of modeling random variables. So let me write it out. Maybe it'll make more sense. So our example is, suppose a very large population of people were asked to rate, I can't believe I did this. This is just a weird example I came up with. To rate how much they love their spouses. on a scale from 0 to 5. Where they can choose any number in that range. Suppose further that they picked all numbers in that range with equal probability. That is, I'm going to rephrase this a little bit, perhaps it'll make it more clear. If I picked a random person from this population, I would expect their score to be any number between 0 and 5 with equal likelihood. So the probability that I observe 2 is just as likely as me observing 2.5, it's just as likely as me observing 3.7, right? All of these numbers show up with equal probability, but the thing that's really sticky is that there are an infinite amount of numbers between 0 and 5, right? So there's not really a meaningful way for me to assign a probability to each individual number because there are way too many for me to do that. So we call the situation a uniform distribution, which is something we've seen before. It's the one that looks like a box. So in this case, if I were to want to describe this random variable with a density curve, it would be, here I need to give myself more space. Look like this. Right? It's the one that looks like a box. And I'm going to tell you now something that you didn't have before. If this lower bound is called A and this upper bound is called B, then the expected value of a random variable when that random variable follows a uniform distribution is just A plus B over 2, or the average of the upper and lower bounds. The variance of x is equal to B minus A squared over 12. And just like other discrete distributions, or maybe I should just say other, this isn't actually quite like the discrete. Probability of x being a specific number, a singular number, is just equal to 0, right? That was just a consequence of our continuous distributions from the past. This is a fact I think even showed up in our midterm. And if I wanted to know the probability of a section, so less than or equal to 3, that is like here around and down, it's equal to just the area under the curve. So in that case, so it's equal to area under curve, which is something that very much showed up on our midterm. Equals 3 over 5. So what did I do here? this is a uniform distribution. This is something that we've seen before. But now the new thing that I'm saying is that if you see a problem that looks like this, you can say, if every single number is equally likely, this is just a uniform distribution. And once you acknowledge that this is a uniform distribution and you know what the upper and lower bounds are, A and B, you immediately know the expected value and the variance. And you immediately know how to answer probability calculations like here and here. Just like with our discrete distributions. But now we're doing it with values that aren't taking on whole numbers, but instead taking on any number between a certain range. Okay? So this is just another probability model. And I want to make one little note. One other new thing I'm going to teach you about the uniform is that the height of the curve. So note I gave it to you here, it was 1/5, but it's actually not hard to calculate. So the height of a uniform density curve is 1 over b minus a, where a is the lower bound, b is the upper bound, of values we can observe. Right, because we can't observe values outside of 0 to 5. They are only allowed to give scores from 0 to 5. Okay. So this is a little bit more information about the uniform distribution. And are there any questions on this? No? So this means that we have completed all of the discrete and continuous distributions that we're going to learn for this class. And this actually will just about conclude our probability section, this lecture, the lecture video, and the next homework. And the next thing we're going to be talking about, which you should get pumped for because it's one of the more exciting things that we do in this class, is inference, which is one of the more applicable things that we do. And I think some of you have a bit of statistics background. This is hypothesis testing is the first thing that we're going to be kind of diving into. So, any questions on anything today? No? All right, well, the lecture video is posted. Your homework should be posted at 4:30, and I believe that is it. So you are welcome to go. Thanks, everyone.
Someone posted a question in the chat.
Oh, thank you. Why is the variances denominator 12? That's a great question. So the answer is not simple. The answer would require you to solve you would have to solve this integral, which you could do. Actually, it wouldn't be terribly difficult, but maybe I will save you that algebra, and if you want, I can show it to you in office hours. But that's why. It pops out when you do this calculation. Cool. Any other questions?